Good morning, everyone, and thank you all for joining us today. My name is Ricardo, and I'm a first-year master's degree student at Polytechnique Montréal. And today I'm going to present an overview of my research project, which is about the study of solidification of aluminum alloys containing chromium and zirconium by using molecular dynamic simulations. Aluminum alloys are widely used nowadays. This is due to their good properties and low weight. Within these alloys, we can regularly find the chromium and zirconium as alloying elements. But why are they important? Let's look at the next example. Some alloys containing small amounts of chromium, such as the 3000 and 4000 series alloys, they present the aluminum 11 chromium 2 as a primary precipitate, in spite of the presence of other elements. Then, the formation of these intermetallics is strongly believed to have a relationship with the short ordering in the liquid state. As an example of short ordering, the icosahedron is presented here, but it'll be discussed later. So, to study the short ordering, we use the software LAMMPS, which is a computational tool to model systems up to the mesoscale, that is, millions of atoms. The main ingredient to model the systems is the interatomic potential. In this case, the Finis-Sinclair EAM potential developed by Liu et al. Will be used to account for the interactions between the aluminum and chromium system. So let's begin with a quick introduction of some important keywords. An icosahedron is a polyhedron with 20 regular faces, and it has a 5-fold symmetry as it can be observed in the animation. Then, an icosahedral structure could be represented by a chromium atom in the core surrounded by 12 aluminum atoms on the shell. The next term is undercooling, which occurs when a liquid is below its freezing point but doesn't solidify. So Frederick Charles Franck was the first one to predict the existence of these icosahedral arrangements as an explanation for undercooling. By doing a two-dimensional analogy, we can observe that atoms in an icosahedron will not line up as a periodic structure. This is due to their 5-fold symmetry, and the case is different if we take squares of hexagons, as we can see in the blue figure. There are two main reasons for us to focus on the study of icosahedrons. The first one is that this arrangement of atoms can act as a nuclei for solidification, which can potentially lead to the formation of twin dendrites as presented in figure D. The second reason is that they could also be found in the solid state. Of course, they are going to be found as a more complex icosahedral building blocks. A suggestion is for an intermetallic, for example, is the aluminum 45 chromium 7 as presented in this figure. There's another model also proposed for the aluminum 13 chromium 2. Now I'm going to present some of the preliminary results from the molecular dynamic simulations. We present here the calculation of the cohesive energy for two different icosahedrons and also for the FCC structure. As an illustration, we can see here the minimization for aluminum 12 chromium, and the minimization is carried out by introducing the arrangement in an expanded box. Then the system is minimized. So from the results, we can see that the aluminum atoms in a pure system from icosahedron are less stable than the aluminum atoms in a FCC structure. Therefore, there's a lot of chances that aluminum atoms in this arrangement will go into FCC to promote the solidification of the periodic structure. On the other hand, we can see that the aluminum 12 chromium is more stable than FCC. So in this case, aluminum atoms will prefer to stay in this arrangement. So in the future, we also want to evaluate the cohesive energy of this cluster in the middle of a liquid, so we can have a more accurate cohesive energy. So in this slide, we present the results from two different simulations. The first one is for pure aluminum, and the second one is for a system containing aluminum and 1% of chromium. Both of the simulations were carried out in 4 stages. The first stage is the heating process up to 2000 Kelvin. Then it's followed by a mixing at the same temperature. Then we did a cooling process, and finally a relaxation at 300 Kelvin. In the second graph, we can see the evolution of the icosahedral fraction for the two systems. In blue, the pure aluminum, and in green for the binary system. At the beginning, the differences are smaller, a little bit bigger for the binary system, and we can see that during the cooling process, the fraction of icosahedral structures increases more for the binary system, which is the green one. We can also see that for the pure aluminum, the icosahedral fraction drops and reaches an equilibrium. This indicates that the solidification has finished. And we can see that solidification finishes in this first video. The first one is for pure aluminum, and as I said before, we can see the whole system solidified. In the other hand, we can see for the binary system, the solidification is slowed down. This is mainly for the presence of icosahedrons that will slow down solidification. So this is why we have smaller grains in the binary system and bigger grains that form for the pure aluminum as presented. So we see also that for the pure aluminum, there's a small fraction of icosahedral structures that are remaining in the system. This can be explained in the next slide. So by breaking down the simulation in different simulation steps, we can see the evolution of the icosahedral fraction in yellow, and also the fraction of the FCC structure in green. We only present these two ordering to simplify the visualization of the ordering. So in general, for example, we can see in image E that there's a transition into FCC in the figure F. So these holes represent the icosahedrons that are solidified or dissolved into FCC to form the grains. Well, in the final step, which is image G and figure H, we can see that the remaining icosahedral structures are mainly in the grain boundaries. So we can see, for example, if we take this grain, there's an equivalent surrounding of icosahedral fraction. So in this slide, we were also breaking down the video into different steps. The first line from A to C represents the solidification of pure aluminum, and from D to H, so the solidification of the binary system containing 1% of chromium. So we can see that after 5 nanoseconds of the simulation, the solidification was almost finished for the pure system, whereas for the binary in figure D, we can see that the 5 nanoseconds were not enough to solidify because solidification got interrupted due to the presence of the icosahedral structures. So even with the 2.89 more nanoseconds, solidification didn't finish, and we have still a region where we have the liquid state. So in this slide, we present the energetics from the transition for an icosahedron to FCC for the pure aluminum. So in the first image, we can see the icosahedral in the middle of an FCC box that is then minimized. So we see the evolution and how it becomes at the end the orientation the atoms has is an FCC. So for each change on the positions, we can see the contribution to the energetic change. And at the end, we have energy release, smaller energy release of 3 electron volt, which is equal or equivalent to 0.23 electron volt per aluminum of atom. The energy release is small, but it is interesting to see because it hasn't been reported before in literature. So in this slide, we present the interlocked icosahedron. So this geometry was predicted after an experimental work by Kuruldu et al. And they used it as an explanation for the orientation of some grains in their alloy, because the orientation of the grains were in agreement with the orientation of these 4 faces in an interlocked icosahedron. Well, it turns out that in our simulation we were able to find something similar. We present in figure A the aluminum in gray and chromium atoms in red. So we were able to isolate this interlocked icosahedron as presented in figure B and C, and in figure D, E, and F we present like different perspectives of this interlocked icosahedron, where we can see its five-fold symmetry. So for the aluminum zirconium system, we were also able to find on literature a recent paper where they present the precipitation of aluminum zirconium. So we're now trying to simulate this precipitate using molecular dynamics. Well, this is the end of my presentation. Thank you for your attention.